Those are online. Am I audible?
Yes, sir.
Okay. So we shall get started, right? So what were the topics we discussed? It's new for you, right? So for today, just try to see. You have to go through the previous videos. Okay. So what were the topics we saw? I think this was the last problem we saw in previous class, right? So we'll get started with the next problem. But before that, let's just recollect the concepts that we saw in the previous class. What were they? One thing is when you need to solve problems which are based on the concept of Lenz's law. Yeah. So when we need to solve the problems that are based on Lenz's law, what are the steps to be followed? Tell me. That's written on the board. What are they? First, you need to understand. So first you need to understand what pole we are. In the sense, if at all the magnetic field lines are into the plane, then what pole are we going to act as? So will be the North Pole and the board is going to be the South Pole. It is going to receive the magnetic field lines. Second, we need to see how the flux is changing. We need to see whether the flux is changing or not. So when the flux is changing, what do you say? So flux is dependent on three parameters. What are they? Magnetic field, area, and theta. So if either of the one of the parameters is changing and the other two are going to be constant, then flux is going to change. So third step is, if the flux is decreasing, then what should happen? Then the pole that is getting generated in this coil should be the opposite pole of what we are. If the flux is increasing, then it should generate the same pole as what we are. And the last step is going to be, if the North Pole is getting generated here, then what should be the direction of current? It should be in the anti-clockwise. And if it is going to be South Pole, it should be in the direction of clockwise, right? So with the same knowledge, what we'll do is we'll start with the next problem. So example 6.5, the question says, a closed loop is held stationary. So there is a closed loop which is held stationary where in the magnetic field between the north and the south pole of two permanent magnets held fixed. So there are two permanent magnets which are held fixed, and in between there is a coil which is stationary. Now the question is, can we hope to generate current in the loop by using a very strong magnet? So what is the answer to this? The answer is a no. How much ever strong magnet you are going to use, unless and until there is a change in magnetic flux that is going to take place. If the change in magnetic flux is zero, then you can forget about the EMF and the current getting induced, however strong the magnets are. Are you able to understand? So in this case, so when the coil is going to be held stationary, first thing, it gives a hint that the coil is not moving. And secondly, it is kept fixed between two permanent magnets where they are also held fixed. In the sense, there is no change in magnetic flux taking place at all, right? Second, there is a closed loop which moves normal to the constant electric field. So what is there? There is a closed loop, and the closed loop is moving normal to the constant electric field. Let's say there is an electric field in this direction, there is a coil, and the coil is moving constantly, and it is moving normal to the electric field. So what is the angle between the aerial vector of this and the electric field? It is zero, right? Now, there is an electric field that is getting generated between the plates of a large capacitor. So there is electric field in this way, and there is a coil which is moving in this electric field perpendicular. Okay. Is current induced in the loop, right? Is current induced in the loop first when it is wholly inside the region between the capacitor plates. What is the answer? So when this coil is inside the electric field, what is happening? The coil is moving, right? So what are all the parameters associated with it? What is going to be the flux in this case? What is going to be the flux in this case? It will be EA cos theta. Am I right? Because here they are talking about electric field, which is going to be constant. So is there any of the parameter that is changing? Electric field is uniform, area is uniform, and theta is also uniform. So there is no change in flux. So can I conclude, since there is no change in flux, there is going to be no EMF induced? Am I right? My thought process itself is wrong. Why? Because when we say change in flux should take place, it should only be change in magnetic flux. Electric field has nothing to do with generating EMF. So the moment you saw that there is a constant electric field existing itself, whether there is going to be a change in flux taking place or not, there is no question of EMF getting induced at all. Because what is changing there? It is the electric flux that is going to change. But what does Faraday's law state? Faraday's law states that I need to have a change in the magnetic flux, not in the electric flux. Is that clear? So read the question again. A closed loop moves normal to the constant electric field between the plates of a large capacitor. Is current induced in the loop? Answer is no. However you are going to place it, answer is no, because change in electric flux can never induce EMF at all. That is answer. Am I clear with this? Right? So they would have asked another question also. When it is partially outside the plates of the capacitor, whatever situation you place, it's not going to get affected at all. Third, a rectangular loop and a circular loop are moving out of uniform magnetic field region to a field-free region with a constant velocity v. In which loop do you expect the induced EMF to be constant during the passage out of the field region? Right? The field is normal to the loops. So there are basically two loops. What are they? One is a rectangular loop and another is a circular loop. Both the loops are moving out of a magnetic field which is uniform. But what is the speed with which they are moving? Speed is v, and if you observe, the speed is also constant with a constant velocity v. Now the question is, in which loop do you expect the induced EMF to be constant during the passage out? In which case do you expect the EMF to be constant is what the question is. Right? Now, listen to the logic. Since both these conductors are moving with the same speed v, so when I say constant speed v, what is the first thing that comes to your mind? It covers equal distances in equal intervals of time. That is the meaning of uniform velocity. Right? Now, if you look at this shape and this shape, both are regular shapes. There is a rectangle, there is a circular, both are regular shapes. Okay, accepted. But what is our expectation? We want the induced EMF to be constant. So if I want the induced EMF to be constant, first thing I need to understand is, here, why is the EMF getting induced in the first place? So for that, I'll write the formula, flux is equal to BA cos theta. So in this case, which parameter is changing? If you observe, it is the area that is changing. Because initially, when the coils are completely inside the magnetic field, the complete area of the rectangular circle is taking the magnetic flux. But as they are coming out, the amount of area that is associated with the magnetic field is decreasing. Makes sense? So when it is going to decrease, there is a change in flux, due to which EMF will get induced, and I want that value to be a constant. Right? So observe, in this case, I can conclude that my EMF generated will be constant if there is something that is going to be constant. Observe what I'm going to do. What does EMF with respect to a conductor's EMF according to Faraday's law state as? E is equal to d phi by dt. I'm not taking the minus sign into consideration. E is equal to d phi by dt. So b cos theta into, can I write it as dA divided by dt? So EMF is equal to b cos theta, because b and cos theta are constant. What is the only parameter changing? A. So area alone should be differentiated. So EMF is equal to B cos theta into dA by dt. Okay, accepted. So my EMF is going to be constant if dA by dt is going to be constant. Means the rate at which the area is changing, if it is going to be constant, then the EMF is going to be constant. In which case do you think the rate at which area changing is going to be a constant? Answer is very simple. It is in the case of a rectangle. Because let's say in 1 second, L unit of rectangle comes out, right? Let's say this height, this width is B. Let's say L unit of rectangle comes out in 1 second. Then what is the area that is coming out? L into B. In the second, what would have happened? Another piece of L would have come out. Then what is the area that is going to come out in the second? It is also going to be L into B. So the rate at which the area is coming out is going to be L into B in all the cases because of constant velocity. Whereas in a circle, what will happen is, it is first this sector which is going to come out, or this arc will come out in the first place, which has a different area compared to this arc compared to a bigger arc. So the size of the arc is going to change, due to which the area that is associated with each arc or area generated by each arc at its center is going to change. So dA by dt will not be constant for this, rather it will be constant for this. Does it make sense? Are you able to understand the logic? So what is the answer? It is in the case of this rectangle, the EMF that is going to get generated is going to be a constant. And what is the reason? You will write EMF is going to be constant if the rate of change of area is going to be a constant. Am I clear with that? And the last question in this is, predict the polarity of the capacitor in the situation described in figure 6.9. If you observe, we know one thing, if the flux is going to increase, right? If the flux is going to increase, what will get generated? Same pole. If the flux is going to decrease, then it is going to be opposite pole. So what the meaning of this is, when the north pole is moving closer to this coil, right? Closer to this coil, then what will get generated is, there will be north pole generated here, accepted? Because when a pole is moving towards a coil, the flux is increasing. When flux increases, same pole should get generated. Similarly, the south pole is moving this side, right? Then there should be south pole that is going to get generated here. So one side north pole, one side south pole. This is something which makes sense. One of the sides it's north, other side is south. But the challenge with respect to these kind of diagrams is, you need to understand how to look at it or how to view it. Okay, for which I would suggest you something like this. See, if you're going to look at the diagram from this side, right, like the way I'm standing and looking at it, use your left hand. If suppose you're going to stand this side and see, use your right hand. Okay, I'll explain it from that side. Right, I'm looking at the diagram from this side. So I'm using my left hand. Now, when I talk about this circular loop, listen to this. So circle, when you see from this side, it will appear like a complete circle. If I take this to be the circle, you will be able to see a perfect circle. If I look at the circle perfectly at 90 degrees, I'll only be able to see a straight line. Whereas if you look at the circle from a certain angle, you will actually be able to see an ellipse. So there is actually an ellipse. Secondly, for this circle, there is a center. So they have drawn these dotted lines, right? Observe this carefully. Whichever side, right? Whichever side you are able to see that the dotted lines are entering the center is the side you are actually able to see. In the sense, if you keep it like this, always keep your hand like this, right? So this is the side where you are able to see the dotted lines entering the center. So you have to turn the coil like this and see, meaning with respect to your left hand, you are actually able to see your palm. Are you able to understand? So there are two sides. I generally define it like that. Listen to this. This is something of my version. One is palm and the side of knuckle, right? So you first keep your hand like this. So whichever side the center is coming, you turn your hand in such a way that you see there's the side where you are able to see the center. So you're actually able to see the palm side. So with respect to the palm, this is A, and this is B. A is at the top, B is at the bottom. Am I clear till this point? Did you understand the theory? So which side am I seeing from? I'm seeing from this side. Whereas if I see from this side, the whole story will be in the reverse. Okay. So I'm seeing it from this side and I'm able to see my palm. Now the question is, since I have my palm having the south pole, so palm is having the south pole. So south pole means current should flow in the south pole means current flows in the clockwise direction. So when current is going to flow in the clockwise direction, listen to this carefully. When current flows in the clockwise direction, A is here, B is here. Outside the device, that is outside the device and along the wire, current will always flow from higher to lower potential. And inside the device, current will always flow from lower to higher potential. Since I'm able to see my palm and the current is flowing in the clockwise direction, out of A and B, which one should be at higher polarity? With the logic that I told you now, I'll repeat it, listen to this carefully. A is here, B is here. Imagine that there is a battery. Actually, it's a capacitor, right? For a capacitor, defined which is the positive terminal and the negative terminal in this scenario. So if you treat it like a battery, listen to this carefully. Outside the battery, current will always flow from higher to lower potential. Inside the battery, the current will always flow from lower to higher potential. So A is here, B is here. Imagine my palm. The current has to flow in the clockwise direction. So current has to go from A to B outside the magnet, outside the capacitor, and from B to A inside the capacitor. So which one should be at higher polarity? A should be at higher polarity and B should be at lower polarity. So this should be positive and this should be negative. You're able to understand? So can we just come from the beginning? Can we just summarize it? First thing, what did we see? When the north pole is moving closer, same pole will get generated. Flux is increasing, same pole. So this side will be north pole. Since the south pole is moving closer, this side will be south pole. So next is, when you're seeing from this side, keep your hands straight, right? Whichever side you're able to look at the dotted lines entering towards the center, turn your hand so that you're able to show that part to the others, right? So you're able to see this part. So when you see this part, this side has south pole. So south pole means current is going to be in the clockwise direction. And we have to remember, for a battery, current will always flow from higher to lower potential outside it and lower to higher potential inside it. So based on that, if you want to decide which is clockwise, then A should be at higher polarity and B should be at lower polarity. So that's what they asked, no? Predict the polarity of the capacitor in the situation described. So this is higher, this is lower. Am I clear with this? Right? So make a note of it. Because you're seeing this side. A is at the top. That's why I told you the diagram is actually given bad. A is at the top, B is at the bottom. அதுதான் சொல்றேன் அது பார்க்காது ஆக்சுவலா the diagram itself is confusing. இப்படி இருக்கு. So for this is A, this is B, right? From A, the current is going to flow in which direction? Clockwise. So it should go into the plane and come out of the plane. இப்படி இருக்கா, you're able to see this side. So this is A, this is B. So current goes from A to B. Clockwise na then இது A, இது B. So this should be the direction of current. This is A, this is B. So இது positive, இது negative. So make a note of it. This new book, old reverse lo கொடுத்திருக்கும். This positive, so polarity of A will be positive with respect to B. Hmm. So, guys, 1 minute, listen to this. So if you see the circle in this way, okay. So this part is cut. There is A here, B here. A is at top, B is at bottom. That point you accept. So A is at top, B is at bottom. So when you look at the circle in this way, the circle is going to appear as a complete one. If you look at it in the perpendicular direction, it will appear like a straight line. Now the question is, I need to see it like this or like this, right? So I'll keep the circle like this, right? I'm just putting it perpendicular to the sheet of the paper. Now what I'm going to do is, I'm seeing, so the center of the circle is here. So wherever the dotted lines are, you are able to see that the dotted lines are coming towards the center. That is the side you need to open up, right? So when I keep the coil like this, so this is the side in which I'm able to see the center. So I'll open up this side. So when I open it up this side, this is A, this is B. This is A, this is B, and this is south pole. Current is flowing in the clockwise direction. So when this is A, this is B, current outside the battery will flow from higher to lower potential, and inside it will flow from lower to higher potential. So that is why this is positive and this is negative. Yeah. Diagram correct தான். அது பார்க்கறதுக்கு அப்படி இருக்கும். The tensity, that problem is that is why I'm stressing this much. If you look at exercise problems, the diagrams are very bad. Hmm. Next. Done with this? Let me know once you're done. Done? Those are online. Are you done copying? Those are online. Are you done copying?
Yes, sir.
Shall I proceed?
Yes, sir.
Listen. So we'll move on to the next concept that is called as so we'll move on to the next concept. It's called as motional EMF from Faraday's laws. Right. So listen to this carefully. We know that Faraday's law states only one thing. What does it state? If there is a change in magnetic flux taking place, there is going to be an EMF induced. Right. So for magnetic flux, again, we have this formula phi is equal to BA cos theta. If you observe, the flux has to change. Either of the parameters can change, keeping the other two constant. So here, as the name suggests, right, when I say motional EMF, right, so the name itself is suggesting that the conductor here is going to be in motion, right? For that, what kind of a setup we need to create is, let's say there is a railing like this, which is in the shape of C, and it is frictionless. On top of which you have a conductor PQ whose length is taken to be L. So though we have the conductor extended like this, we are going to take only this length because these are the ends across which the EMF is expected to get induced. Okay. Now what will happen is you're going to take this railing, which is again a conductor only, it's a conducting material, on top of which you are going to make this conductor move. It is free to move and it is frictionless. The surface is frictionless. Now what is going to happen is, if suppose you take this whole setup of this C type and the conductor and place it in a magnetic field of uniform value, and you are able to create a scenario where this conductor is either able to move to the left or to the right? Then you can observe that EMF is going to get induced across this conductor. And that EMF which is going to get induced is what is named as motional EMF. Okay. Now our job is to find out what is going to be the value of that motional EMF that will get generated. Okay. Let's observe. So here, there is a magnetic field which is existing into the plane of the paper, right? It is in this direction. So the board is acting like the south pole because it is receiving the magnetic field lines. Now we have a conductor which is moving with a speed v, and the speed is going to be constant. So it is moving with a constant speed v in the leftward direction. Now tell me one thing. When I say phi is equal to BA cos theta, which parameter in this case is changing and which two are constant? First thing. Magnetic field, if you observe, it is uniform, right? They are equally spaced. It is uniform. So B is constant. It is not changing. What about the orientation of the coil? If the aerial vector is into the plane, then the magnetic field is also into the plane. So the aerial vector is also going to have the same orientation with respect to the magnetic field. So theta is also not changing. But what is changing here? It is the area. Why is the area changing? Is because by us placing this conductor here, you are actually able to form a rectangular shape. In that rectangular shape, the length of the conductor is fixed. But the distance from the fixed end to the conductor, that is this x, is going to change with respect to time as the conductor is moving towards the end or moving away from this end. Am I clear with that point? So all that I need to do is, first I need to write the expression for flux. So what is the flux here? It is BA cos theta. I am writing the basic formula. So what is the value of B? Let's keep it as B only. What is going to be the area? Area is going to be L into X. So it is going to be L into X into cos of how much is going to be the angle between the B vector and A vector. So it is going to be 0 degrees. So since it's a two-dimensional shape, we can take whichever direction we want to be as the area. I'm taking into the plane as the area. Okay. Minus d phi by dt, but I know that the minus sign is only a significance of Lenz's law. If I'm able to find the polarity, then I can find only the magnitude of EMF. So for this minus, what I will do is I'll apply the Lenz's law and find the polarities of which is positive and which is negative. Okay. So d phi by dt means it is going to be d by dt of B into L into X. So B into L can be taken out because they are constant. So B into L into d by dt of X is going to be B into L into V. So this B into L into V, why I wrote dx by dt as V is because the rate at which the distance is changing is going to be the speed. So dx by dt, I wrote it as V. And this value is what is going to be the EMF that will get induced at the ends of this conductor, the pink color conductor. And this EMF is what is called as the motional EMF. Am I clear with this point? Now, the important thing that I need to understand is I understood how to find the magnitude. All I did is applied the formula for flux, differentiated it, I got the EMF, I got a value, done. That is all we need to do. That is all the derivation part is. But the most important thing is finding the polarities, right? So for finding the polarity, we already know what are the steps to be followed. What is it? First, when you stand in front of the conductor, you need to identify what pole you are. Since in this case, the magnetic field is received by the paper is acting as the south pole and we are the north pole. Second case, you need to observe whether flux is changing or not. Obviously, flux is changing. It is clear. That is why we got the EMF. Third, if the flux is changing, you need to identify whether the flux is increasing or decreasing. When the conductor moves to the left, is the area decreasing or increasing? look at the value of x. L into x is area. When the conductor is moving to the left, is the x value decreasing or increasing? Decreasing, right? So when area decreases, flux should also decrease. So what does it state? When there is a decrease in flux taking place, what pole will get generated? Opposite pole of what we are. So we have to remember, since the board is south pole, I am the north pole. Opposite to me is going to be south pole. So there will be a south pole that will get generated in this loop. So if it has to be a south pole, the current has to flow in the clockwise direction. So we know that this conductor is the one across which the polarities are going to get generated. Now this conductor is acting like a battery. So what did I tell for a battery will happen? Outside the battery or outside the cell, current will flow from higher to lower potential, and inside the cell, it will flow from lower to higher. Since the current is flowing in the clockwise direction, this is supposed to be at higher potential, and this is supposed to be at lower potential. Okay, one common mistake that happens is some of them write this as higher and this as lower. Don't do that mistake. So always remember this logic. For a cell, current will always flow from higher to lower outside it, lower to higher inside it. Am I clear with this point? Now what I will do is, you first copy this, then I will prove that this is negative and this is positive using some other law as well. Okay. Are you done? Are you done? Yeah. So now what we will do is, so from the concept of Lenz's law, we are clear with the fact that P is going to have negative polar, P is going to be negative and Q is going to be positive. Am I right? Now the question is there any other way to find the polarity of these points? That's what we are going to see. So thing is, I have this situation and this point is P and this point is Q. This is the conductor and this conductor is moving in the magnetic field which is directed into the plane in the leftward direction. Am I clear with that? So now I'm going to concentrate only on the conductor. So if I take the conductor into consideration, what is present inside a conductor? You have free charges, that is free electrons. You have the free electrons. And remember, when the conductor is moving in the leftward direction, can I say that this electron is also moving in the leftward direction? Right, as of now, there is no polarity that has got generated. So when the conductor is moving in the leftward direction, the electron is also moving in the leftward direction and the field is into the plane. From the fourth chapter, we know the fact that whenever there is a charged particle moving inside a magnetic field with a speed v, then the force experienced by the charged particle is given as Q into V vector cross B vector. Am I right? So Q, if you observe, it is going to be minus E into the speed of the particle is V, but since it is in the leftward direction, it is going to be minus I cap cross B is into the plane. So I'll write it as B of minus K cap. Am I clear with this? So minus of minus here is going to be plus. So I will take the scalar parts outside. So minus EVB into I cap cross K cap. Minus EVB into I cap cross K cap. So if I take the circle, this is I, J and K. I cross K is going to be minus J. So this clearly indicates that this is going to be minus EVB into minus J cap. So minus of minus in this case is going to be E into V into B J cap, right? So let's just try to summarize it. What did we see? We have a conductor. Inside a conductor, we know that there are free electrons, and this conductor, when it is moving the leftward direction inside a magnetic field, the electrons present inside the conductor will also start experiencing force, which is given by the formula Q into V vector cross B vector. In the place of Q, I wrote the electron. So electron has a negative charge, so put minus E into V vector is going to be V in the direction of negative. So B of minus I cap and B is into the plane. So it is B of minus A cap. So on solving this, we get the final expression as EVB times J cap. The meaning of this is this electron, which is moving the leftward direction inside a magnetic field into the plane, is experiencing a force in the upward direction. So when it is experiencing a force in the upward direction, that clearly tells us that all the electrons are going to get drifted towards the top. So when they get drifted towards the top, more amount of negative charge is concentrated at the top. So this will become negative and there will be a lesser value of negative charge. So this will become positive. And this is another explanation for us to give that P is negative and Q is positive. Are you able to understand? Right? So this also clearly validates that P is going to be negative and Q is going to be positive. Okay? Yes. So just make a note of it. Done with this, right? So now we will try to understand how to find the direction of induced EMF in this kind of a scenario by using a rule called as Fleming's right hand rule. Okay. By using the Fleming's right hand rule. So it states that this rule is going to give you the direction of induced current set up in a conductor moving perpendicular to a magnetic field. So if there is a conductor which is moving perpendicular to a magnetic field and you want to find the direction of induced current, you can use the Fleming's right hand rule. Okay. So how to use it is something similar to the Fleming's left hand rule, but it is going to be in the other way. So you take your right hand, right? So you're going to stretch your first three fingers, that is the forefinger, the central finger, and the thumb mutually perpendicular to each other in such a way. If you observe, the forefinger is going to be placed in the direction of field. So forefinger is placed in the direction of field. The thumb is going to be placed in the direction in which the conductor is moving. So forefinger in this direction, thumb in this direction. Now, when you extend your thumb, correction, I'll come from the beginning, listen to this. So first, extend your forefinger in the direction of field. The thumb is to be extended in the direction of motion of the conductor. And when you stretch your central finger, the central finger is going to give you the direction of induced current. Forefinger field, F and F. Thumb is the direction in which the force is there. So conductor will move in the direction of its force. That is by motion. Okay. And central finger is going to give you current. And that current is given a suffix called as induced current. So why is Fleming's right hand rule used? To find the direction of induced current in a conductor which is moving perpendicular to the magnetic field. You cannot find it in random direction. So you need to ensure that all these three are going to be perpendicular to each other. Field and motion should always be perpendicular because you're keeping your fingers in this way. Am I clear with that? Right? So make a note of this. Generally, when a conductor is moving, here you talk about a loop that is moving. There'll be a loop actually. You will not apply it here. Generator and the Mary devices, there will apply. Now, if a loop is explained, you will not understand. This rule is defined for a conductor only. But obviously, you cannot have conductor which is open to have induced current in it because you need a loop. So, when a loop the loop it is made up of four conductors. Across the four conductors, you want to find the induced EMF. This will help you. Induced current, sorry. Here. Shall I proceed? Hmm. So in this problem, if you observe, there is a metallic rod of length L is rotated at an angular speed omega normal to a uniform magnetic field B. Okay, first let's draw a diagram for this. So there is a magnetic field which is directed into the plane. See, they didn't give us in which direction the magnetic field is there. I'm just taking it into the plane. Okay. So there is a uniform magnetic field like this. In this, what is placed? There is a metallic rod of length L that is placed. So there is a metallic rod of length L that is placed. And what is happening to this rod? This rod is not moving, it is rotating. There is no translatory motion, rather there is a rotational motion. So if there needs to be a rotational motion, one of the ends is supposed to be hinged. Right. Now, let's say this is revolving in the anti-clockwise direction with an angular speed omega. Am I clear with this? Right. So metallic rod of length L is rotated with an angular speed omega normal to a uniform magnetic field. Let's take this to be the scenario. Right. Derive expressions for the first thing. You need to find the EMF induced in the rod. Meaning, when this rod is going to rotate, what is going to be the EMF that is going to get induced across the ends of this rod? Secondly, you need to find out what is the current induced in this current induced in this rod. And the third is you need to find the amount of heat that is dissipated if the resistance of the rod is taken to be R. The resistance is majorly given for you to calculate current and heat. If it is only EMF, you don't need resistance. Right. So if you observe, the first question that we need to answer is there a change in flux taking place in this scenario? And the answer is yes. Because when this rod is rotating, right, let's say it is rotating with a desirable speed, it is covering some amount of area in each time interval. Because it is rotating with an angular speed omega, right? It is going, you can take it as a constant value. And it is going to cover certain amount of distances in equal intervals of time. Right? It is going to cover some area. Now, our job is to find what is the area that is swept by it in a small time interval, and then we will integrate it. Okay. Let's say it has moved from here to here, which covers an angle of alpha in time delta t. Okay. Now, the question is, how much is the area swept by it? Listen. First point to be noted here is, since you're talking about angular speed here, this is going to be measured in terms of radian per second. So the angle is supposed to be in terms of radian, not in terms of degrees. Right. So when I say there is going to be a revolution of 2 pi radians, what is the amount of equivalent area that is covered by it? When the rod rotates through an angle of 2 pi radians, what is going to be the amount of area swept by it? It is going to be pi r square. When the angle is going to be alpha, how much is going to be the area swept by it? We don't know. So that is going to be alpha divided by 2 pi into pi r square. So pi and pi will get cancelled. It is going to be equal to half times r square alpha. So when the rod is rotating from here to here, when it is sweeping an angle of alpha at the center, the area covered by it is going to be half into r square alpha. So if I am trying to define the flux here, what is going to be the flux in this scenario? Flux is going to be BA cos theta. Here the magnetic field is uniform. Let me call it as B itself. What is the amount of area swept by it? It is half r square alpha. But tell me, what is the value of r here? The radius of the circular loop is nothing but the length of the rod itself. So what I can do is I can change r square as L square. So B into half L square alpha into cos of how much is the angle between the magnetic field and the aerial vector? Again, it is going to be 0. So cos 0 is going to be 1. So it clearly tells us that we have half B L square alpha to be the value of flux. But what do we need to find? We don't need the flux, we need the EMF. So we know that EMF is equal to d phi by dt, or this is also going to be equal to half of b L square into d alpha by dt. So what is the rate of change of angular displacement? That is called as angular velocity, which I will write it as omega. So this is going to be half b L square omega, and this is also called as motional EMF. This is also called as motional EMF because this is getting generated across the ends of this conductor. Why I call it as a conductor is because they use the word metallic. Metals are conductors. So across the ends of this conductor, I am able to generate EMF due to its motion. So there are two formulae that you need to remember. One is BLV. BLV is going to come when the conductor has a translatory motion. Half B L square omega will come when it is having a rotational motion. So this can be remembered like a formula itself. Okay. So if you see, you can treat it as a problem, but on the other hand, you can treat it like a derivation for a formula also. Okay. This is the amount of induced EMF. Then what about the amount of current? I is equal to E by R. So E by R means it is going to be B L square omega divided by 2R. This is going to be the induced current. So just divide that value with R. And the third part is they're asking the amount of heat dissipated. So for heat dissipation, the formula is going to be I square RT. What is I square? B square L power 4 omega square divided by 4R square into R into T. R and R will get cancelled. It will be B square L power 4 omega square, the whole divided by 4R into T. This is the amount of heat that is dissipated. Is the point clear? Okay. Make a quick note of it. Okay. Have you done? Those are online, we can wind up.
Thank you, sir.
Yeah.